So one thing that I would like to ask, the audience is, have you ever been in a position that maybe you have a product that you bought and then maybe there are some problems with your product and you need to repair it. Maybe you need to know, how can I, deliver this back to the store and get a new product? And you find out that, there's no phone and no email address, but there's actually a chatbot that you can use. And then you start chatting with the chatbot, but you can never reach, to the conclusion, what should I do with my product? And then you get more and more angry, and the chatbot, he just asks you, in a polite way, so what can I do for you, ma'am, or what can I do for you, sir? And all of a sudden, you just want to take your piece and just throw it out the window. Did any one of you experience a similar situation? So it could be...
it sucks, actually.
So, one big problem here is that, the systems and devices that we're using on an everyday basis, they don't actually understand us. They don't understand our emotions. But what if we could actually change that? What if we could make systems and machines that can use emotions, that can make use of our emotions in order so that we can interact much better with them? So that's actually the topic for today's talk here, which is called Affective Computing, how we can bring humans and machines closer through emotions. And now we talked a little bit here about my background here, but I've been working for 10 years with human-machine interfaces for process automation and robotics. And my educational background is a master's degree in electrical engineering and also a master's degree in behavior science. I'm always been in this intersection between technology and psychology or behavior science. And I'm interested in artificial intelligence and Internet of Things. And I'm also quite involved here. I have an MVP, a Microsoft MVP in AI, and I'm also part of the Oslo AI user group in Norway, and also part of the Norwegian.net user group. But the topic here for today is affective computing. So what is affective computing? We can say a short explanation here is that it's the human side of AI. And a little bit longer explanation is that this is systems and devices that can recognize, interpret, and simulate human effects, or what we call emotions. So basically this, how can we use emotions so that we can have much better interaction with machines, but also with ourselves from human to human. But in order to understand this, we need to first understand what is actually an emotion. So the things that we talk about in our daily language as an emotion can actually be three different concepts. So the first one is from psychology, what we call emotions. They are fast automatic responses, and they are temporary, and it's a react to something called a stressor. And these emotions, they are common to all people. Then we have something that we call feelings, and with feelings we mean something where we actually need to use our cognitive awareness. So we are aware of the environment and the emotion. So this involves a thought process, and it's also much more long-lasting. And then we have something called affect and mood, and this is when we mix feelings and emotions together. So this is a much more complex thing, and this could also be long-lasting. Now I'm going to go through some of the most common theories of emotions that we've had here throughout the history. So one of the earliest theories of emotion comes from 1880. So it's from two researchers called James Lang. So what they said is, what has happened is we see something external, an external stimuli that will give us a physiological reaction. So our emotional reaction is dependent on our interpretation of this physiological reaction. So for example, if you're out in the woods and then all of a sudden you see a grizzly bear, then you will get a physiological reaction. Your body will start to tremble and your heartbeat will start to race. And according to this theory, we will interpret these physiological responses and conclude that you're frightened. So you're not trembling because you're frightened. They say that this is the other way around. You feel frightened because you're trembling. So this would mean that in order for us to feel emotions at all, then we would actually need to have a physical experience of that emotion. But we can clearly think of a situation where that cannot really be true. So if we move forward here in time to 1920s, there was a challenge to this theory by two other researchers called Cannon. They said that we feel the emotion and this physiological response at the same time, And what happens in the brain is that there is a region called the thalamus. It will send a signal to the brain that results in a physiological reaction. So you see a snake, and then you're afraid and begin to tremble. So people, they will experience the same physiological response to different emotions. So for example, sweating and heartbeat and respirations, they all are the same, both for fear, for excitement, and for anger. And in this model, the emotion and the physiological response, they will occur independent of each other. Then in the 1960s, we had something called the two-factor theory of emotions, or the cognitive theory of emotion. Here is the focus here is on the interaction between two different factors, the physiological response and also the cognitive labeling of that response. So for example, here's a situation: if you're alone, you walk in the parking lot, and then all of a sudden there's a strange man that appears and approaches you. And what will happen is this: first you see a strange man appearing, and then you will feel that your heart is racing and you start to tremble. And then this rapid heart rate and trembling, they will be caused by fear. So this is a conclusion by a process we call cognitive labeling. And then you conclude that you're frightened, that is the emotion. And then one of the more later theories is from the 1980s, which is called the cognitive appraisal theory. And according to this model, what you do is you do two different kinds of appraisals. So the first is a primary cognitive appraisal, where you ask yourself, what does this mean? So you can think that maybe this is not important, or this is a good thing, or maybe this is very stressful. And then after that, you have something called a secondary appraisal. So then you can either have a positive appraisal, you can say that, oh, I can actually do this if I do it my best, or if this fails, I will try another method. Or you can have a negative appraisal. Then you think that, oh, I can't do this, I know I will fail, so I won't even try it because my chances are too low. So an example here is, again, you're out in the woods and you see a bear, and then maybe your primary appraisal is, this is very stressful. But then your secondary appraisal can be, I can escape. So the emotional experience of fear and physiological response. Now, when we know the basics of emotions, then we need to figure out how can we actually measure emotions. So to find the origins of this, we have to go back a little bit in time to the late 1800s. Then Charles Darwin, he wrote a book called The Expression of the Emotions in Man and Animals. In this book, he claimed that emotions, they are universal across the human species. And he also said that emotions actually has an evolutionary history. Then in the 1860s, there was a physician called Duchenne, and he wanted to make a book with facial expressions so that he can look up what kind of emotion is my patient experience just based on the facial expression. So what he did was, in order to get these expressions, he was using probes on his patients, electrical probes with a weak current. So then he could stress the facial muscles so that he could get his patients to react in different types of ways with different grimaces, as you can see in this picture here. So what he did was he published a book with 60, where he said that he could identify 60 discrete emotions from facial expressions. And this is a little bit important here, because if we fast forward another 100 years, there is a famous American psychologist called Paul Ekman. So what he did was he conducted studies on facial expressions and emotions. So he went to Papua New Guinea, a remote island, to study facial expressions. So he found an isolated tribe, and he found evidence that facial expressions and emotions are actually universal. So we developed something that is still used today, which is called the facial action coding system. So this is used when you do behavior studies. Then you can look at something that we call micro expressions in the face that will reveal what types of expressions you will experience. So how can we do if we want to detect these emotions? So there are basically three main ways for emotion detection. The first is facial and bodily expressions. So by the way, here are these different kinds of universal in this picture. So the three main ways are either facial and bodily expressions, or you can study the speech, you can study the tone, the intonation, the pulsation and rhythm, or you can use physiological based measures like measuring the EEG or the heart rate or the skin conductance. So now when we know a little bit about what is an emotion and how do we measure it, then we can move into effective computing. So effective computing started in the 1990s with a researcher from the MIT Media Lab called Rosalind Picard. She published a book called Affective Computing, and when she did that, she started a whole new field of research. So by now it has its own IEEE proceedings, as well as international conferences and multiple research groups all around the world. And what she said in this book was that we should be able to use machines, that the machines should be able to sense the emotional state of the user. And it should do so by using sensor cameras and microphones. And it should use speech recognition, gesture recognition, and image recognition. And in addition, we should be able to use machine learning in order to make sense of all of these types of data. So in the 1990s, the state of the art of the computers, they were not in the form that we could actually make any commercial use out of this. But as you all know, machine learning and AI is a huge topic today. And the reason for that is some enabling technologies here. So one of them is that we now have access to smart sensors where we can have real-time data flow. And we also have big data solutions that we can do transformation and storing our data in the cloud, for example. And we have machine learning algorithms that we can scale very fast horizontally and vertically also in the cloud. And for us as developers, we have API and services that we can just use in order to use this in our own applications. I'm actually going to show you two small examples here of what we can do. So the first example here is something called a face detection API, which comes from Microsoft. It's a part of something they called the cognitive services. So basically you have an image as an input, and then it will give you a rating as to what is the most probable emotion that this person is experiencing. So let me switch over here to Chrome. So if I can get my pointer in the right place. So what you do if you want to use this, then you can go into the Azure Portal, and then you can search for face. And then you can just create a face resource here. And then after that, you need to assign it, to a resource group, and you need to define in which region is this going to be, and the name, and what kind of pricing tier you want to have. So I've done all of that. And then what you get then is you can use test console. So here I have an image, which is one moment there. Yeah, which is over here. So this is an image of a kid which looks quite surprised there. So if we take this URL and then we paste it into the test console, which is this, then we just make a regular post here over to our face detection service. And then what we get there is, first we get the rectangle here, which defines where is the face actually in the picture, and then we get the attributes of this face. So we can get an emotion rating here. So here we can see that it's very probably it's 83% probability that this boy was experiencing surprise. So, and then you can also do similar things here on sentiments analysis too. So then instead of sending in a picture, you will send in a text into this service, and then it will detect is the text mostly positive or is it negative. And you can do this, for example, if you have a set of reviews, maybe you have a restaurant or a product and you want to know what is sort of the general consent about my product, then you can use sentiment analysis in order to understand if people in general are more positive or negative. Now I'm going to show you a couple of application scenarios where we can use this. So one of them is within retail. So you can think about, we have a store, a clothing store, and then you can have cameras in your store that are registering the facial expression of your customers, and then they can use face detection analysis in order to determine the emotions of the customers. And then the staff in the store can use this information to enhance their service and give a much better experience to the customer. You can also think of a medical scenario here. You can use physiological based measures to determine the emotional state of the patient and be able to reduce the stress. And also the medical team could be able to respond much quicker to the needs of the patient. We can also think about education. In an educational settings, the teacher could use cameras to detect the emotions of the students through the facial expressions. And then he can see if the majority of students are feeling bored, maybe the teacher could change his method of teaching. And this could also be applied in an online setting by use of web cameras. One problem here in our Western world is that we have a growing population of elderly people, but we don't have enough of workers that can help these elderly people in the daily life. So in Japan, they have done experiments using robots to socialize with the elderly using both facial recognition and speech and tone evaluation, so that the robots can adjust their behaviors towards these elderly people. So what is in the front line? So I want to show you an example here, which is called Effectiva. So Effectiva also comes from this MIT Media Lab. So what they say that they have the world's largest emotion database. So they have 6 million faces across 87 different countries. And what they do for us is that they offer this as an emotion SDK and also an API, so that we can integrate their technology in our own products. So some example of use cases can be, you can have a virtual assistant that can recognize the emotion of the user, so it doesn't happen what I was talking about in the beginning of this talk. Or you can think about the personalized transportation experience. So let's say that you have a self-driving car, and then the self-driving car can adjust the route and the music and other things in order to accommodate the mood of the passengers. So if he sees that the passengers are in a good mood, he can take the scenic route. Or if he sees that the passengers are in a bad mood, he will just take, the shortest possible path between the 2 points. And it can also be used in advertising. So one of the important things when you do advertising is you want to be able to elicit a specific type of emotion at a specific point in time. So it's really important to understand if this advertisement will create the right emotion at the right time, and you can use this for that. That's also been used in cars to analyze the head tracking movement, so that we can issue a warning if a driver gets drowsy and is about to fall asleep when he drives the car. Then we can issue a warning so it doesn't cause an accident. And here's another example called Pepper. He's a robot developed by a Japanese robot company, and he determines the emotions of people around him, both by utilizing voice and face recognition, as well as body movements. And they can respond by changing the color of his eyes and the tone of his voice, and also what is displayed on his tablet. And it's been used by, for example, in large bank in Japan, and also in the railway stations. And as a fun fact here, he is actually using this Effectiva API that I was talking about just on the previous slide. So a lot of people are talking about artificial general intelligence. And what is that? So artificial general intelligence is when we see that the machine can perform any intellectual task that a human can do. But we're not in that stage right now. So what we're in now is something that we call narrow intelligence. So that means that our machine learning algorithms, they can only solve a very specific problem. So the question is here, will we reach this general intelligence, and how can we actually detect that we've reached this stage? So we have some operational definitions of artificial general intelligence. One is the Turing test, which was developed in the 1950s by Alan Turing. And in this test, we say that a program will win $1 million if it can fool half of the judges into thinking that it's a human while it's interacting with them in a free-form conversation for 30 minutes and interpreting audiovisual input. And then another definition here is the coffee test. And here we say that an AI should be able to go into an average American house and figure out how to make a cup of coffee. And this includes identifying where the coffee machine is, what does the different buttons do, and finding the coffee in the cabinet, and so on. We have also something called the robot college test, and this is when a robot can enroll in a human university and take classes in the same way as humans. And we have the employment test, and this is when a program can have the potential to completely automate economically important jobs that humans are doing right now. The question is, what does the future actually bring? Is it a threat or is it a hope? So we can have a look at what people have said. So Elon Musk, he was a little bit negative. He said that we are summoning the demon that AI is our biggest existential threat. And we had Stephen Hawking. He said that actually full artificial intelligence can spell the end of the human race. Then we have one of the pioneers within machine learning and AI, Marvin Minsky. He said that once the computers get controlled, we might never get it back. But it's also important to, to calibrate to see what did they say and what did actually happen. So in the 70s, there were two researchers that said there was a popular thing called symbol systems modeling, and they said that this is the answer to everything, that we actually need to alert the people because symbol systems modeling will take over the whole world. But that didn't really happen, so they didn't need to alert the people. And at the same time, there was also something called the rule-based systems. So Japan used a lot of these rule-based systems. So some researchers said that Japan will dominate the world because they're using this rule-based systems. But that didn't really happen either. But what does the research community within machine learning, what do they think? So there's a researcher called Max Tegmark. He made a survey among the research community, and he was asking, when will AI have this super past human level intelligence? And if this happen, will it be a good thing or will it be a bad thing? So you can see that there is quite different opinions. So if you ask them, will this happen in a few years? There's virtually nobody that thinks that. Will it happen in a few decades up to 100 years? Then we can divide them in 3 different groups. The Luddite, which thinks this is definitely bad. The digital utopians, which thinks this is definitely good. And then people who are in between. And then there are also some researchers that think that this will not happen in the next 100 years, and probably not in 300 years, or maybe never. So we should also touch a little bit about the ethical AI. So there's a test here called the moral machine. And what you do here is that you imagine a situation where you have a self-driving car that approaches a zebra crossing. And then there are different situations. What should the self-driving car prioritize? So should it prioritize humans over pets, or maybe passengers over pedestrians, or maybe more lives over fewer lives, or women over men, and so on. So they have done this in over 200 different countries. So what they found that this actually varies a lot on basis of the culture, on basis of the economics, and the basis of the geographic location. So let's have a quick look at some of these questions here. So this was a question if we should save these young people in favor of the old people. So we can see here that individualistic cultures like the UK and the United States, they're much more in favor of saving the young, whereas more group-based societies like Japan and China, they want to save the old people. Or we can see here, should we save more lives or fewer lives? So here, the United Kingdom and United States, they want to save more lives, whereas China and Japan, they want to save fewer lives. Or should we spare pedestrians over the passengers? So we can see, for example, Japan, they want to spare the pedestrians, whereas China wants to spare the passengers. And what is important here is that we can see, if we as the human race, we can't really agree on what is actually objectively morally right or wrong, then how can we expect that machine learning algorithm or an AI could actually take morally right decisions? So this is an important thing to take into account, and also especially when when your AI will be highly affected on where it actually is produced and where it is trained and manufactured, because this will really sets its imprint on how you can use your machine learning algorithms, and what it will decide is a morally right thing to do in a given situation. So now finally, I just wanted to touch upon something called collective intelligence. So collective intelligence is nothing new. It has been known for a long time that a group of people have a much higher chance of achieving great results than a set of individuals. So then there were some researchers, they set out to try to find, can we find a single factor that is called collective intelligence? And they first thought that maybe it would be correlated to the IQ, to the average individual intelligence quote of the participants. but they only found a moderate correlation. Instead, they found 3 main factors. So the first factor is called the average social perceptiveness. And this is a test that you can do yourself online. So what you get is you get a set of images where you can only see the eyes of a person. And then you should be able to read the emotions just by seeing the eyes. And then the second factor is called participation in group conversation. Here it's important that you don't have any dominant person in the group, that everyone should be able to speak their voice. And the third factor is the proportion of women in the group. They found that more women, the more intelligent groups. And this has to do with the first factor that I was talking about, this social perceptiveness. So what this means for us is that we as individuals, we need to be good at working together, have high interpersonal skills. And for computers and machines, we need to design these so that these computers can work well with us humans. And that is what effective computing is all about. So then finally, I have some references if you want to know more about this interesting topic. So the first reference here is the book Affective Computing that was written by Rosalind Picard. And then the second book is a book called The Blueprint for Effective Computing by Klaus Scherer and Tanja Bensinger. And then we have something called the Oxford Handbook of Effective Computing by Calvo, Dumello, Gratch, and Kappas. So with that, I would like to thank all of you for attending this talk. And if you want to know more, if you have any questions or comments, you can always reach me either on Twitter, where I'm called Gravlis, or you can reach me on my email address that you can see here on this slide. So thank you so much for listening to my talk.